All right.
They're rather more exotic.
Yeah. Okay. So what I was going to do today. Thank you, Max. All right. So I'm going to do basically a quick review of flat state machines, hierarchical state machines. All right. So that would be a flat state machine, and let me just do one thing here, so make it 10 attention, enable extended monitor, yes, got it. Okay, and hierarchical state machines, okay, and then how those go together inside the ES framework that they're going to be using from Lab 0. So the Roach is going to be done. Roach is going to be within ES framework. All right, and also we're going to show you the 2 additional capabilities we've added, which are the, is it inject keyboard events or use keyboard events?
Use keyboard events.
Use keyboard events. So we'll see it when we look at the code. There's a use keyboard events, which solves the problem of how you do unit testing of your state machine, because now you can inject events to any state machine from the keyboard, and it ignores all others. So that is, and the tattletale.
It still might take timers now to develop things by Thursday.
Yeah. So this is inject events. And then we've got the tattletale, and the tattletale shows you a state event trace. And this is going to be, you will see it will spew a lot at you because you're doing a lot even when you don't think you're doing a lot, because of the way it works. So we're going to go through it, and hopefully I'll have some time to, we'll look at the templates as well. So we've done some framework templates that anybody can take and modify for their use. All right, so the example we're going to use to do this, so let's first talk about state machines very generally. All right, so state machines, in case you do not remember, right, the idea of the state machine is we have a, so here's our initial transition. This is initial transition. And sometimes there's something you want to do there, some action you want to take. Coming in, we have a state. The state can have an entry and an exit function. And this is actually, didn't really use this in the past a whole lot, but now that we've sort of got it working, it's really slow and very convenient. Because if you do the same thing coming into a state all the time, no matter where you come from, then it's really convenient. It's really convenient to just shove it in the entry function, and every time you enter that state from outside of it, it goes in. So then we will have, from this state, we will have a transition, right? So we'll have some event that triggers a transition. The event can have with it an action. The event might have a guard, all right? So some conditional that you want to check, and then it goes into another state, which also has its entry and its exit functions. Yeah, so things like that that we can take a look at, and there might be, there might be 3 different things that it goes to, right? And this one might come here, and that one might come back, and this one might come around there, and that one might hook to this one. As states tend to do. All right, so you guys are familiar with the state machine, and that's sort of the idea. Now, so that's our standard flat state machine. And it works fine until the problem, a nice simple problem works okay. Right? As soon as the problem gets a little less simple, right, then all of a sudden it starts to get not okay. All right, and then you get the famous state explosion problem, which is if you really start to be careful about keeping track of all the different states, you wind up with hundreds, and when you wind up with hundreds, it becomes difficult to sort of manage where you are remembering the same thing. Okay? So one way to manage the complexity of the state machine is to go from a flat state machine. This is a flat state machine because it's only one level. The other way we can do it is we can go to a hierarchical state machine. And this one has the concept that the states have depth. which means that I have the same thing. So I have my initial state transition, my state, and maybe that goes to another state, and maybe that goes to yet another state. All right, and maybe this one comes back this way, and there's a different transition here. Okay, so I have relatively simple things. And then what you can look at is you say, look, inside here, I have yet another state machine. That sits inside it. So we have to think a little bit about how this mechanism works. Right? So the way we get to do this is you handle events at the lowest level, and it might very well be, by the way, that this state right here has yet its own little state machine running inside. So that goes 3 levels. Right? And the idea is that you need to be able to handle events at the lowest state possible first. So you send the event all the way down as deep as you can. Right? You see whether or not the deepest one consumes the event, if it handles it, if it takes the appropriate action. If it doesn't, it says, I don't do anything with this event, this is not my event, and it hands it back up to the higher level. So what that means is you go depth first, right? So you go in, down first, and then you come back. And at each step you come back, you give that level state machine the opportunity to consume the event. If the event is consumed, that's flagged, and when it comes back to the upper level state machine, it says, I don't have an event anymore. No event exists. What it also means is that the lower level state machine can then, for instance, it can say, hey, my reaching a certain state is in itself an event. And that means that if I get to this little state here, right, I'm going to post an event back to the top and say, hey, I got here. Right? Because that triggers it to do something else. Right? And so ordinarily, right, what this allows you to do effectively is program by difference. So the super state handles all the things that are common, and the substates handle that which is different. Now, this is all nicely abstract, and I'm sure it makes absolutely zero sense at this point. So what we're going to do instead is we're going to do an example. Right? And the example that I chose, after looking around and sort of bashing my head for a while, the example I came up with is my electric toothbrush. And what's interesting is that my electric toothbrush is, so it's a Sonicare, right? And I didn't even include all of its behavior. I included most of its behavior, because if I actually tried to include all of its behavior, I would have already had the state explosion problem that we've got a little too complicated to show you. So what I did was I did it both as a flat state machine and as a hierarchical state machine to show you that you can do it both ways. See, and we're going to sort of look at the implementation and see how it goes. All right, so the basic idea of the toothbrush is it does a couple of things. When it's in the charger, all right, it blinks the LED when it's charging, and it's a steady on when it's charged. If you ever put it in the charger, even if it's running, it immediately shuts down, right, and goes into charging mode or charged mode, whichever it happens to be. Right? When you pull it out of the charger, it's just off. It does nothing. When you push the button, so nominally it's off. When you push the button, the motor starts vibrating the bristles. Right? And then, every 30 seconds, it hiccups. Right? Which is it pauses for about half a second, right? To let me know to move to a different part of my mouth that I'm brushing in. Right? And then after 2 minutes, so after 2 minutes of brushing, it shuts back down again, comes back to the off state. Okay? And that's like this. Now, you can pause it. If during your brushing, you hit the power button, it stops. If you let it go more than 30 seconds paused, it resets and starts from 2 minutes again. However, if you turn it back on, it continues exactly from where it left off. No, it's just a standard. I mean, it's the way it works. Turns out that sometimes you need to sort of pull it out of your mouth and say something or do something like that or put it down for a second. But if you're done brushing, it sort of starts, it doesn't want to hold 5 minutes. Right? So by that time it figures you need to start over again anyway. Now, there's a few other sort of things. So these are the sort of basic features of the toothbrush, right? There's a few other things. For instance, it has a whole bunch of different things that it does when the battery gets low, where it comes on briefly and turns back on and beeps 5 times and things like that. And I was like, yeah, okay, that's a little complicated, so we're not gonna look into that. But this is a pretty basic, simple toothbrush. So with that, let's see if I can bring up Omelet here.
You should be able to double click the state machine.
Yeah, if I can find it.
It should be open. One of them should be open. Here, HSM and FSM.
There it is. Program toothbrush. There it is. Okay. So here's the flat state machine. All right.
Yeah.
Was that? No, I know. So when this comes up, I should be able to move it across. Okay. Boom. All right. So, yeah. There it is. Hold on. That's right one. Okay.
And then close your pane.
I don't know how you can close it.
You can just grab the area and slide it.
Yeah. Let me get my mouse coming. There we go. There we go. That's as small as it's looking. Okay. And so let me zoom out a little bit. Okay. So.
Look there, I think so.
Okay. So here is a little bit more. Okay. Okay. So here we go. So here is our state machine. All right. Now I have here on the reset brush state, which is a count set to 0, stop the hiccup timer, stop the main timer, set the hiccup timer for 30 seconds, but don't start it. Set the main timer for 2 minutes, but don't start it. Okay. So this is my reset, which we're going to be doing a lot. Now, it doesn't have a whole lot of states. If you look at it, really only 5 states. All right. So there's the off state, which is normally where it comes in, where it resets the toothbrush. All right. There's the brushing state, and I can get to the brushing state. Notice there's only one arrow going in, and that's the button press, and it stops the resume timer, right? Which is when you get to. So if you're in the paused, if you pause it, you're back in the off state. While the resume timer going, if the resume timer expires, you actually do a self transition back in and reset the brush state. Right, that's what this little doohickey is here. All right. So while I'm in brushing, when I get a timeout on the hiccup timer, I reset the hiccup timer for half a second. I get to reuse the timer since it's the only reason. So now I'm in the hiccuping state. When I'm in the hiccuping state, when that timer expires, I come back to the brushing state. And notice that the entry into brushing is turn the motor on. So, and the exit from it is turn the motor off. Which means I don't have to ever worry about turning the motor on or off, because if I'm not in brushing state, the motor's off. And if I'm in it, the motor's on. Right? Because I came in. So that's kind of cool. And the other thing is here, I have to start the main timer and start the hiccup timer as I go in. The entry to this one is increment the count. Right? So I've got to increment the count, start the hiccup timer, and then on the exit, I set the hiccup timer for 30 seconds. Right? And then when I enter to brushing, I start it again. Right? So here I set it, there I start. And then you can see that, if the main timer times out, I'm back to off and I reset the brush state. If the hiccup timer goes off and the count is greater than 3, then I'm also coming back here, right? So that coming back to off because it will hiccup 4 times. The 4th time it hiccups, we're done. Right? We've gone 2 minutes. If I'm in either the brushing state or the hiccuping state and you press the button, then I start the resume timer, I halt the hiccup timer and halt the main timer, right? Now notice I have to halt the timers, but not necessarily reset them, right? And I start the resume timer, and again, if the resume timer goes, then I reset, and when I reset, I include killing everything. If you press the button again, however, it stops the resume timer, right? So the resume timer doesn't then go off and post-minus timeout. Right? So that's sort of on the brushing side. And then we have, if you stick it in the charger and the voltage of the battery is greater, then it transitions to the charging state. And if the voltage is greater, then you're already charged. And so here the LED is on, there you blink the LED. I did this in a little cheesy way, which is I just have a timer that's periodically going off and it keeps checking. which is not the correct way to do it is to have it as an event checker, right? And so the event is charged or is not charged, right? Or basically so that you fall above the threshold or below, and that will move you from one to the other. So I don't have to do this continuous timer check, but in any case. And again, if it's either in the hiccup state or if it's in the, I forgot one. If it goes on charger from the brushing state, it should also go to here. So I have yet one more transition in here that I noticed I did not include. All right. So needless to say, yeah.
For the on charger voltage battery, which one would have been less than? You've got two greater than.
On charger greater than should go here. This should be on charger less than. Right? And we can. So just so you know how this will work, if you've ever done, we can just. This is omelet. Okay, and then it changes it. All right, so there we go. So as I said, there's another line that I have to bring from here out to both of these. And as you can see, even though it's only got 5 states, it's a mess. It's a mess because everything goes everywhere, and we can do it. But let's stick with the mess and let's see what we can do. All right. So since we've got the mess and we're happy with the mess, let's take a look at. Okay, so we've got the toothbrush flat state machine. All right, and we modified this from the template. So there's 3. There's a template FSM, a template HSM, and then a template sub HSM. And you'll see the reason is there's a slight difference between the superstate and the substates because the superstates get called by the framework in a slightly different way than the substates do. So we and there's a .c and a .h for each of them.
Can you have an FSM and an HSM or a sub HSM or
simultaneously? Of course, there's different services, absolutely. Okay, we have up to 8 services that we're doing, although our processor, other than, and I'm going to say this and get Max to blow his Mountain Dew out his nose, but it's just a small software change, right? But in order to go sort of from 8 to 16 or more services, currently we only do 8.
There's a lot of places you have to change code. It's simple, but you have to
find people all. Yeah,
no one should.
There's a lot of bookkeeping. There was a group at Stanford last year that went through all 8 and needed more. But they were doing something odd.
That's Stanford.
Yeah. Well, the other thing is, interestingly enough, is they actually have a much harder time. They're using a lot less capable hardware than we are. And so they actually have to shoehorn things into a smaller size, which is interesting. So the first thing I'm going to show you.
That's a lot of code complexity what they do.
Yeah. Okay. So here is MPLabX, as we know and love, and we're looking at the ES configure. So, well, I
Get
want
rid
to
of tasks. You put the X on output.
this one right here.
No, the other. Click that one.
Yeah.
Then click that one.
This X.
Yes.
Okay.
And there you go.
Okay. That's even better. What I was going to do first was I was going to file, open project. I want to show them the templates first, which are in an odd spot right now, but they'll get better. And
No.
yeah, that's where I have.
Oh, you just put on something weird.
Yeah. Okay. I just want to show them the templates. Okay. So let's look at the template FSM. Go away. Okay. So here is the flat. Here's this. Let's start with this header file. Okay. So here it is, the header file, and there's a whole bunch of things you'll need to know this. The reason you're going to need to know this is because the kids are going to try to modify them, and they're going to get completely lost. And I need to walk you through. I'm going to show you what the template looks like, and then show you what happens when I change the template so that you can see it. So a bunch of things are going to change. So first of all, this FSM template needs to be changed, all right, to something more appropriate for their project. I put in these nice little comments to tell you this should be changed, all right, but that doesn't mean it's going to. All right. So here we have the ES configure.
Would you show them how to refactor the view?
Yes.
Doesn't work.
But it won't work on that part. No. It works in a couple of places, not there. Okay, so the first thing is, notice that we have...
Search replace would be probably repair that, then refactor, just search replace a new project.
All right. So what we've got here is we've got our state variable, and here we have a template state type. All right, and notice that it's a type def enum, and very important, this first state should always be init state, and it should stay init state. Init state never changes. All right, and then all of the others you get to name them whatever you want. Okay, and again, you're going to change that. So here we have the function prototypes, and again, these are going to change. So we use for the return values of true and false, we use an unsigned 8-bit, so an unsigned car. And so here we have init template FSM again. So if you read the actual comments, right, it says, right, this will be called the framework at the beginning of the code execution. It will post an ESIgnate event, the appropriate event here, which will be handled inside run template FSM function. Remember, we named this to something appropriate. Okay, returns true if successful, false if it's. All right.
And if it's false, your program shuts down.
Yeah, if it's false, everything dies. Right? Because at that point, you said, I can't init the hardware. Everything shuts down.
Will Tattletale let you know where they're shut down?
Oh, no, the framework will let you know.
Even
before Tattletale even begins to run. Okay. All right, this is, you're not even getting close. Right? You're out. Okay, same thing with the post template. Again, you're going to rename this. This is how you push events to the queue, and it takes an ES event type. All right, the query template just simply is a wrapper function that returns back whatever state you happen to be in up there.
And your first glitch you'll have, that init state needs to be unique.
Yes. So one of the things every project, which means you're going to have to sort of dig in and change things a little bit when you go through.
If you try to run multiple state machines, those enum names need to be unique.
Yeah. So all
any P station.
Well, no. P state will have to change.
Yeah, that'll have to change to something else, and you'll have to alter it in your init code in that template.
I mean, wait, we changed the state but not names.
No, you have to change the state name
if you have
parallel state machines.
If you have parallel state machines, then you'll need to alter that because enums have to be unique. Okay. In other words, even if it's in a different file, right? If it's a different file and the headers are included, then if the compiler can see both, they have to be unique.
So we should just tell them to always have unique enum.
Yes, although
one of them has to be in a state.
No,
not if you have parallel state machines. If you have multiple state machines running, then no. If you have a hierarchical one, leave it as an init state. All right. Okay, so here we have the init template. We have the post template function, the query template function, and then where everything is going to happen is going to be inside your run template state machine. Okay, so that's where it is.
They don't even have to call post and query.
Oh yeah, they do. That post.
Event checkers, that's how you get to the state machines post template.
Yeah.
You call run only on lower level hierarchical state machines.
Right.
You don't call it on the top level, but on the lower levels.
The framework will call run for you, right? But it needs to know what it is, and I'll show you where that's in once I get to the framework.
Once you just see the toothbrush example.
Yep, you'll see it. Okay. So here is the actual implementation, all right, as we go through. And again, so here is the template state, current state starts off in init state. Okay. Make sure that you change this to match it to whatever you change the other one in the header file to, or you will have a problem. Yes, and you change the pound include up there. That should be that also gets changed to the right name. Okay, and then all of these names, of course, change. So let's take a look at the init template. So all it does, remember that this gets called, because it's a flat state machine, this gets called by the framework, and the framework handles what priority is because it's assembling which queue goes in which order. Okay. So basically it says, right, my priority is equal to priority. It's basically set in this module level variable that's up here. Okay. It's going to set that one, right? Current state is going to be init state, right? It's going to start it there. So which means that might be a little redundant, but that's okay. And then it's immediately going to post a service with my priority and this init event. Right? And it's going to say, if it's true, that means the init worked, then return true. If not, return false. If it returns false at that point, it breaks the framework. The framework errors out and does it. Same thing, the post is just a wrapper. Right? So whatever you named is going to be post to service with priority and this event. Right? So it's just it just sends it through to the other one.
You might want to show them what an event is.
Yes. I'll take a look at okay, so let's see. To get there, I right-click on that.
Control is the easiest.
And go to
that works.
Declaration or implementation? Declaration. Okay, so here is an event. All right, and this is the. I'll show you that this is the wrong ES event because we have another one that. No, what about the init event, init timeout, and
That's the right event type.
that's the right event type. Yeah, it's not the right ES events.h, but this is the right one. So again, it's got a type which is an enum, and then a 16-bit parameter that you can set it. Okay, so hopefully you guys remember that from last time. All right, so this is just a wrapper. The query just returns current state. It's very important for the tattletale to work that you leave current state always the name current state. Because we rely on that, actually. Okay, and then here comes the fun run one. So this is where the state machine gets implemented. Okay? So again, you're going to rename all of this. Right? You're going to rename run template, but we've got our unsigned 8-bit make transition is false, whether or not we're switching states. Okay? The template state type, again, you need to rename that to whatever your right enum is, of the next state. And the reason we need to do this is in order to implement those entry and exit functions, this function, run template, gets called recursively twice. Okay, it gets called, so as soon as you know that you're going to make a transition, you need to, before you make the switch out of your current state, call yourself with an exit event, and then switch states and call yourself with an entry event. Right, so that's how you have to do it in order to have the correct order of cleanup, which is you exit your current state and then you enter your next state, and both of those have to happen.
Why don't you transition on exit?
Because it's not the same thing, right? You actually need to exit your current state with an exit event. And then you need to enter the next state. You need to then switch states, enter the next state, and call that next state with an entry event so it executes the entry at that point. Yeah.
Can those events be
nothing? Yes, absolutely. In fact, most of the time you'll probably find you do nothing with them. Okay.
Oh, I see it.
But the call has to come in case you do so. If you do nothing with them, it falls through, hits the bottom, falls right back out, and that's it. Right? In other words, okay, so let's take a look at it. Alright, so the ES tattle. Okay, this is where the magic happens. Okay, and we've got a very clever pound define. So if you're not using the tattletale, that becomes a blank line. Right, and if you are, it becomes a nice, nasty little function that is really quite clever. We're not even going into how it's implemented because it really is a little bit bizarre.
So the line actually disappears.
Yeah. No, I mean as far as your code goes, you'll see it, right? But the line actually will disappear in compiler code. Right, in the compiled code, it doesn't exist.
Oh, you turn it off.
Right. So in other words, this is actually a pound define that gets pound defined to something else, which is a very complicated function call. Exactly. And you don't see. Okay.
It becomes a semicolon.
So here's the first part, which is switch on current state. So the way we implement this is nested switch statements. All right. So we switch on current state. So in the case that it is in init p state. Okay? And again, if you have multiple parallel state machines, you would have to change this init p state, and you would have to change that init p state along with the enum, to something else. That would, or else it won't do. Now, when you're in init p state, the only event it should respond to is an ES init. It should respond to nothing else. Okay? Nothing else. Nothing else would go. So in this case, we have an if this event, dot event type is ES init, right, then this is where you put all of your code where you make a transition, and then you change your current state. Now, you have an option here. Okay? If your current state, if you're going to switch to your first state, if you want to do an entry into the next state, right, then you would actually do a make transition equals true. You would tell it, I'm switching states. If you just want to move it to the other state without executing its entry event, which you might not, depending because its initialization is sort of a special case, right, then you'd leave it as I did right now. So if I wanted to switch state and actually execute the entry function, what I would do here.
Just go down to the next.
What about the exit function?
Yeah, just go to the next. Go to one of the ones that actually does it.
Okay.
Can you explain what we make transition?
Make
transition.
We'll get to it. Okay.
We'll get to it. It's going.
So in this case, right, this is just a it's a template, right? Alright, so and a lot of this is going to become a lot clearer once I show you the example as we go through. Alright, so so we switch to the first state. So here's an entry where we don't do anything. So break, here's an exit, we don't do anything there. So this is keep event. So this is an example where the state does not transition. So I'm just going to do this event, dot event type is ES no event. That tells the event has been consumed. I've done whatever I want to do with it. And then I send it back that I've consumed this event, the event is no longer active. Okay? And then here's some other event, right? In this case, next state is other state, which is going to pop me out from first state to other state. And make transition is true. Okay, which means I'm now going to switch states. Right? All these three above here, none of them were switching states. Okay?
Make transition.
No.
Make transition is for the frame. It's for the recursive call for entry and exit.
Okay.
You know.
So
Yeah, it was.
It was.
No one used it.
No one used it, but it was there. Okay.
So when you set make transition to equal to true,
Yep.
so when it's gonna call this run,
It will. You will.
and it's gonna.
It's later in the code. We have to
Yeah.
get through other states because that drops out that giant switch statement.
Right.
And then we have to drop all the way down.
Okay, and then it executes exit.
I'll show you. Yeah.
Well,
You'll
it's in
see
the
it.
code.
You'll see it. Just be patient. All right. So basically, I mean, you could, instead of doing this make transition is true here, you could actually just check if next state isn't equal to your current state,
And
that way.
Interjection on tail.
Mhm.
None of this except the ES title and tail calls and some array definitions have anything to do with tail.
Yeah.
All of
This
this
is
is just the state machine.
This is just a framework and a state machine. Okay.
We'll go into tail what exactly it
All right.
wants.
So from first state to this break right here, this is all the state first state. An entry, an exit, keep events, other events. So all the events that it responds to are within here. And then any event where you don't do anything goes into the default, which does nothing. Okay, so there's two switches, right? So you're in the tops level switch, which is switching on state, and then within each state you do a switch on event. Okay, so that's always, it's always a state event there. So here's the same thing with other state, very similar, you'll notice. Okay, and so we get to those two. So I only have two in this. I have first state, other state, and then we hit it. If make transition is true, okay, this means we've switched states. Okay, we haven't switched it yet, but we are going to switch states. If that happens, okay, then I need to make the recursive call. I need to run the template from my current state, which is, we're still in my current state, with the exit event. Okay. Then I switch states. Then I call it again with the entry event. All right? So that is the only way to get the guaranteed cleanup where you exit all current states first, then move to the new ones, then enter all the next states.
Slightly overkill for the flat state machine.
Yes, but nonetheless, if you want to do, the clean entry and exits to your states, and we use them and they work really well. So you'll see an example, and then every ES tau that's up at the top, right, gets its corresponding ES tail. All right, so it's tattle and tail, and when tail runs, essentially tail will fill up a buffer and then dump it to the screen so that you can see what's going on.
And as long as they have title on top, tail at the bottom of every
They should never have to alter it. It's within the template.
We have templates, follow the templates only, do not
Right.
make your own.
So if you're altering the template, the only thing that you're going to be doing is you're going to be changing the names of the states and the names of the events and filling this in. All right. So this is a flat template. So now let me take a look at what one looks like. Okay. Let's go. Okay. So let's look first at the ES configure to show where the names of everything goes. All right. So a couple of things. So these are important. Pound define, use keyboard input. Okay. This tells us which, if you want to use the keyboard inputs, this is for testing, and you put 2 slashes in front of that, you're no longer, put 2 slashes in front of it, and you're no longer using the keyboard and it runs normally. Same thing, post function for keyboard input. Which state machine do you want the keyboard events to hit? Okay, so in this case, we're going to go to the toothbrush flat state machine. Okay, and again, this pound defined use tattletale. Right? So if we want to do that, and then we have this other one, suppress entry and exit in tattletale. If your entry and exit functions don't do anything, all of them, if you decide not to use them, make sure this is defined and it'll just ignore them. It won't spew. Because remember, every transition is now 3. Every time you transition, you get your exit, your entry, your exit, your switch, and your entry, right? To where you get there. And so it expands a lot.
I should have asked this before you transition, but in the flat state machine, any event that happens within the state machine before it exits, is that consumed?
Yes.
Even you don't want
That's the definition of a flat state machine.
it has to be consumed.
Right. Once you call it, that means you posted it to its queue and it gets consumed.
Okay.
Definition of flat state.
That's the definition of flat, just one level deep. Right. So, okay.
Can you explain what the kind of that defines process
If you're not using the entry and the exit, because you've decided that, I'm just going to code the actions and on state transitions on yourself, and you're not going to use the entry or the exits, then you're going to get a lot of output from the tattletale that's going to give you the function name with
Every time
entry
you
and
do the
exit.
state transition, you get 3 tattle calls.
Right. And so if you're not using it, then we can suppress it so that the output doesn't.
So you don't get a whole bunch of exit
Exactly.
entries.
All right. So in this case, we've got 3 services. Our usual one, which is our timer service.
And there's documentation on this. This is just a slide review.
Right, so this is that. Service number
These will be reordered.
1. Right. So here I have my toothbrush flat state machine as its header file. The init function is init toothbrush flat state machine, and the run function is run toothbrush flat state machine. And I never expect to have more than 3 simultaneous events, so my queue is 3D. Okay, that's where it goes. And then normally, so we'll probably swap these 2.
We're swapping those.
Yeah. So the keyboard is always going to be 2, and then you start at number 3, essentially. So there we go. And so here's the keyboard input. And again, a init keyboard input and a write keyboard. So the keyboard input, by the way, is just another service. All data, right? And this one we gave ourselves a larger queue. We get 9 going in. Okay, and then right, and then here we go. So here there's nothing, none of the rest are defined because we don't have any more. And then here's our post key function. Yeah.
How would you decide how many or how large will each size be?
Generally, you make it as 3 is pretty good first ballpark guess. If you find you're losing events because you've got multiple events coming simultaneously, frankly, on our processor, you shouldn't unless. So, for instance, on the timer one,
We have the timer is the largest.
okay, the timer is 9, and the reason the timer is 9 is we have 8 user ones that can all go off simultaneously.
Technical definition is that you need how long does your state machine take to run? As there's no blocking code, it should be fast. You need the minimum time to actually, how many events can you generate during one run of your state machine?
Right, and that's the size of your queue. Alright, so, and then the part we get to here
And these also might be reordered a bit.
yeah, things will probably move around the file, but this is it. And so again, we have sort of the standard ones, which include no event, error, init, entry, exit, key inputs, list events, timeout, timer active, timer stopped. And then my user events, in this case, button press, on charger, out of charger, done charging. Right? I don't even think I used done charging in this case.
It doesn't matter which word.
No, it does not. They get pulled from here and defined because you're using a case state. It doesn't matter at all.
You just start stuff after ES list events.
No, after
sorry.
Right.
Yes.
So right here where it says user defined event start here, everything you want goes after that. Now, this little thing is the one that's generated by the auto hotkey. We need that for Tattletale. So it basically,
if you're not running Tattletale, it doesn't care.
It doesn't care, but if you are running Tattletale, you highlight this one, run the auto hotkey script, and paste below it, and it will generate all of this so that you have the text of the things. And this is so we could actually get the names back rather than giving you numbers, which you would then have to trace back. Exactly.
What's
What's that? It's an auto hotkey
It's going to
script.
be a desktop. It's going to be a desktop icon. You copy that. You double click it. It'll tell you where to paste it,
And then you paste it.
and then you paste it.
And it's just,
You can't just, okay.
You can enter it in by hand, but the odds of entering it in by hand and getting it wrong.
I installed Hotkey on this one, so you could actually just run it.
Oh. Cool.
If you want, but I don't think it's worth it.
We'll do it on the other one if I got it wrong. Okay. So, yeah, so you can do this. The reason we did that was because we didn't want you to have to do anything funky in typing this one in. And generating this to match that each time, it's easier to automate it than it is to that force you to type it incorrectly. Because if you type it wrong, that's what Tattletale is going to spit out at you. So if you have it wrong, you're going to really get confused. All right? Okay, and then the rest of this is...
And if thing dies with Tattletale on, just does not respond, quite likely it's those two lists.
Right.
The list of events has to be in the same order. Right?
It will generate it automatically.
It'll generate it in the same order.
Yeah.
It generates exactly that from that. So each time you add events and want to use Tattletale, you just have to run the script again.
Yeah.
Okay. Which you probably won't be doing that often.
No. All right, so then the last thing we have is, which the event checker is toothbrush-events.h. Here's the check event list, the comma separated ones, so check buttons, check charger status. Now, because I'm just running this for debugging, I actually don't have, let me just show you what they look like. Oh, I'll close that one up.
Except in long.
Yeah. All right, so here is a toothbrush events .c, and if I hit the .h file, okay. So here they are. Basically, check buttons, check charger, check status. They all return true or false, right? They return false if there's no new event, true if there's a new event, right? And if we look at it, in this case, since this is kind of a throwaway, they all in fact return false, right? So that's it. Because those are going to get called as fast as they can in order, right? Until an event comes, and once an event comes, then it posts the queue and it runs the appropriate machine. Right? So you need to know what those look like. All right. So back on our ES configure here. All right. Let me get rid of that one, and that one, and that one, and that one. Okay.
They return true if there is an event?
Yes. True if there's an event, and false otherwise. So here I have my 3 timer functions. Right? What's that?
No.
All right.
Let's check something.
Which are post toothbrush FSM. Okay, so those are my, remember that post function we defined? So there they are. And it says, by the way, when the timers go, this is who they should post to.
The event checkers do return true or false because they handle posting to the state machine they care about themselves.
Right.
That's why they return true or false. It just, all the true or false is for is we're going to break the event checking loop when the event happens.
Right. So, because we're going to run through and we need to know, once one of them is true, we've got an event and we need to break out of it. That's why it has to return true.
Okay, so the first one called has the highest priority.
Right.
Yes.
And then the next one, what's going to do is to call each event checker in order, in a round robin, until one of them hits true, and then it breaks out, and then it runs all the services who have something in their queue. Right? It's going to run all of those until there's nothing left in any of the queues, and then it could go back to checking events again.
And it will, the Roach FSM main we give you will show you some basic events.
Yep. All right, and so here, in order that I not have to use timer 8, timer 7, I basically give myself, main toothbrush timer is 8, hiccup toothbrush timer is 9, resume toothbrush timer is 10. Okay, so there are my timers. All right, so that's the configure. All right, so now let's take a look at the flat state machine.
I have a question about that.
Yeah.
So does that mean we want them to call the most frequent events last?
Makes no difference because they're being called in order. It won't call them twice. It'll call them.
No.
Each one gets called in order, and it breaks out as soon as one.
It breaks as soon as one. So
right.
There is a priority to them, but remember that events in the framework are on transitions, not for some state.
Right.
You don't have I am currently bumped. You have I was not bumped. Now I am bumped.
Right. So I went from was bumped to not bumped to was bumped, right? And all of a sudden that's an event. Right, the event is always the transition. So you're never holding an event generating spewing events.
Okay, so it's not able to never block them.
No.
In general,
never
it's got a very fast block.
Yeah,
In a very fast event you can, but it's rare enough that's not to worry about.
Alright, so here is, so we took the template and we've now modified it. Right. So now, because I don't have the rest of the code,
It doesn't actually have a toothbrush.
it doesn't actually have a toothbrush, so I just put in a whole bunch of place motors so I could see what I was doing. So brushing motor off, brushing motor on, turn charger on, turn charging off, LED steady on, LED blinking on, LED on. Right? So these are the actions that I wanted to take. And in order to, the neat thing is I can test it, I can test the state machine without actually doing anything real. I don't actually have to have the rest working. I just need the keyboard. That's all I need. And that's pretty cool. All right. So again, we have now I have a private function prototype in here of reset brushing state. If we go back to Umlet, you can see that reset brushing state right up there. I call this a bunch of different times, and so I wanted to consolidate the code into one spot rather than, what's that?
It's just helper subroutine.
Yeah, just a helper subroutine. That's all it is. All right, and and here's the prototype for it, and the actual definition of it is way down at the bottom. All right. I have some variables I need to keep track of. So I have my toothbrush state, right, which starts out in nitp state. My priority stays the same. And here I have my hiccup timer count that I need, and my toothbrush battery voltage that I'm because I'm checking the battery charge in a cheesy way. Okay? And then this state names comes from, that we need for the tattletale, and that comes from the enum definition as well. Alright, so here we are. We've changed this from init template FSM to init toothbrush FSM. And again, no call on the inside of it gets changed other than the name. That's it.
This is also in place for one-time only hardware initializations if you want.
Yeah, if you've got things that you need to do to sort of set up the hardware, this is where it goes. Actually not there, but in the run I'll show you what.
It should be there most. It depends where you're in block or hierarchical.
Exactly.
In flat, it doesn't matter. In hierarchical, it does.
It does. Okay, and then here we have our post toothbrush FSM, query toothbrush, and here's where the fun happens. Okay, so this is where we're going to implement everything. So we're run toothbrush FSM, and notice that we're now in toothbrush state type. Right. Next state.
This is an overview. We're not going to go through all the states to show what it is.
All right. So in my initialization, right? Again, it only responds to ES init, and one of the things it needs to do in init is reset the brushing state. If I look at my Umlet again, right, there it is, right there, reset brush state on my initial transition. So I reset it, my current state goes to off, and I don't need to do a transition and exit out and an entry in on initialization because nothing happens, because it's already going to start with the motor off. I'm not worried about it. But if I wanted to, I could make the make transition equals true, in which case it would go through and call off with its entry state to enter into off on entry. Okay, and I chose not to do so here. All right, so case off, we have on entry, we turn the motor off. On exit, we stop the timer. In case of a timeout, I have to check if it's the resume timer. Right? If it is the resume timer, I reset the brushing state, and I pass back no event, which means I stay in off. I just reset the brushing state machine. Okay. And then if it was a button press, okay, then I stop the resume timer. The next state is brushing, the transition is true, and I've consumed the event. If it's on the charger, if the battery voltage is greater than fully charged, then it goes to charge state, else it goes to the charging state. In both cases, it's made a transition. It goes through, and then everything else does nothing. Right. If I'm in, is that?
A brief overview again, not every state.
All right. Same thing. And
we just also have the HSM.
Yeah. Okay. So as we go through, so here's sort of basically from the diagram, it's almost a straight translation to this. All right. So again, here we have, if we're in the brushing state, it depends which timer goes off. So here we respond to, if it's the hiccup timer, we do one thing. If it's the main timer, we do something else. Okay, so there's our thing there. And again, and so we go through all of this. Here's where on entry we implement a count. So basically it's just a pretty straight implementation of everything we've done. All right. And it goes through, and this is, as I said, almost a one-for-one translation from where we've got. And so now we can go ahead and build this guy. And if I pop this guy in, interesting on-the-fly demo. Oh, yeah. Yeah. Well, we'll get to see whether or not the tattletale and the whole thing works. Okay, so we're successful. All right. And now, this does not appear to be plugged in.
It is not. We're having chargers having issues.
Charger's on.
Yes, but the light's not on. Now it is.
Oh, okay.
There's a glitch in it. I don't know what it is.
Got it. No, it's...
Like I said, pull it here. You have a wire or something that's starting to fray inside somewhere.
Okay.
As far as I know.
Yep. All right. So now we're going to run the DS loader. All right, we're going to flash this. So let me get this to the... All right.
Oh, what the hell?
What?
No settings.
Alright.
All right. How do I get
View
this?
advanced mode.
Advanced mode, okay.
Reset. Reset first. Tab. Reset.
Reset, there we go.
ETR.
ETR.
10.
All right.
And then basic. Let me see if we can get that up. And then pick device.
Slide 1. There it is.
And baud rate. It's the mark one.
115.2. And the port.
This thing did have,
Okay.
you know,
Column 0 ports. 0. Oh, you know what I bet it doesn't have?
no, it does. I know because I've actually opened it with this thing.
Mm-hmm.
No, not device manager. Device manager is not on thing only.
Mm-hmm.
Okay.
Column 4.
I'm holding it because it didn't know about it until it actually started.
Got it.
Which unfortunately will do settings if that's easy.
Yep.
Right. You like to go this way for a reason.
Okay.
Okay.
All right.
That
So
page again. The
yeah,
whole thing over again.
Advanced.
Reset.
Reset. ETR. 10.
And all the students have to do this to every computer they're on.
Basic device. That one. That one.
Yep.
Oh, but it has to be on their user.
Yes. Now let's just check for bill right now. Or get the COM port.
There it is.
And
Okay.
just check bar rate for anything else.
Done.
Okay.
Okay.
Now you can get the hex file and we're all good to go. Only won't auto switch right now.
Like the
Yeah, we'll get there. All right. Dropbox. Sandbox. That one. Build.
Nope.
Oh.
Backup, distribution.
Distribution, default, production. Got it. Okay. And then under terminal, I know, before that I want to switch this one to
Switch to left to right.
switch to left to right and okay.
Let's hit right flash. Down to.
Or off that one. Okay. Okay.
That doesn't matter.
Okay. And here we are. Okay. So now we're actually running. We're starting a toothbrush state machine, right? Using second generation or type 0. Run toothbrush ES init 0, printing all events available in the system. All right. So these are all the events that we can go. All right. You can redisplay by sending a 6. So if in here I type a 6 semicolon.
Yes.
Okay. And then
Enter.
Enter. Enter. All right. It will list events.
Oh, 14 is odd.
Yeah. I might not have gotten the one right. But
Yay, Brian. It's IIT.
it's IIT. But all right. So let's so let's go ahead and We didn't pick up the initialization.
Yeah, we did. It's up. It's before the first print.
Oh, there it is. So there, okay. So here's what we saw. It ran run toothbrush FSM from init p state, and it sent it an es init and 0. Okay, an es init with a parameter 0. All right. So there was your first trace, and that was all it did. It came back, and now it's in state off. So if I send it an es timeout, all right, so I'm going to do a 7 semicolon. Now 7 in this case arrow, and I need to tell it which timer went. So let's say it's the resume timer, which was, I believe, 10. All right, so now when I do this, okay, it says es timeout with parameter 10 was passed to post toothbrush FSM, right? And it said run toothbrush was in the off state, got es timeout with parameter 10 and did nothing, as we expected. Okay. So now let's see what happens if we do the button press.
It's much more fun when we actually have something happen.
So now something's going to happen. So the button press gets no parameter.
Parameter is in hex.
Yeah.
Just so you know, the events are in decimal, but the parameters are in hex just to actually, they can be a lot larger.
Right. So you can put any parameter you want in there. Okay, now we go. All right, and there's a lot of output we need to suppress still, but here's the basic gist of it. Okay, so now button press with parameter 0 was passed to. Okay, and this is some debugging stuff that we have to turn off. But here's what happened. So run toothbrush FSM was in the off state, got the button press, which turned into an exit event from the off state right there, which then calls the brushing state with an entry event. Okay? And
that's essentially the recursive call you
that's
get
the
every
recursive
time.
call, right? So that's one transition.
Next 2 lines will be suppressed eventually.
Right. So this was because we turned the timers on. The timers, it basically spat back to us that you just have 2 timer actives, right?
You don't want to consider it?
Well, that's an event if you're on keyboard input, you actually don't want to see that event.
Oh, because you don't want events generated.
Well, no, because also timer active just means you turned it on. It's an event that we don't actually care about. It was more for us debugging.
You could actually use it if you wanted to.
We could use it if we wanted to, we're not using it, so these 2 events get produced because that's produced from the entry to ES entry. So ES entry gives an ES timer active and an ES timer active for 9 and 8.
It starts both timers.
Because it starts both the timers when you go in.
Right.
Okay. So now, moving on, let's see what happens. Now, I forgot what state I'm in, right? So I need a list events, right? So I'm going to pass it to 6 again. Probably should make that a question mark. If we make it a question mark, that would be... No. Anyway.
I need it the same.
I know. Okay.
I need the same on the code.
That's true. All right. So here is, I list events again to remind myself what events I can send in. Oh, right. Okay. So I'm printing all the events, and so the next one I want to do is a timeout on the hiccup timer, all right, which is either 8 or 9. I have to look at my code to see. And so if I go back to my code and look at ES-configure,
Yeah, the source list. Or the list.
Yeah, there it is. So I look at ES-configure.h and put that at the very, very bottom. All right, I say, the hiccup timer is 9. So we started both the main and the hiccup, which makes sense. And now let me get back to here. Okay, so now I'm going to put my hiccup timer. All right, so that's going to be 9. So it's going to be an ES timeout event, which is 7. And the parameter is 9, because that's the hiccup timer. And
The event is not parsed unless you have the semicolon, just so you know.
So if you don't include that semicolon at the end, it doesn't know what it is.
It's just waiting for events still.
All right. And so now we got a good one. All right, so this was, brushing, run toothbrush FSM was in state brushing, received ES timeout with parameter 9, went to run toothbrush FSM brushing ES exit, went to run toothbrush FSM hiccuping with ES entry, and entry itself generated another event, which was ES timer active, because remember, it resets the hiccup timer and does it again. Right? And
why
so
does that goes arrow, it doesn't do an arrow for the last?
Because this is actually a different call. This is actually, it's exited, it's because timer active posted.
The timer active posted then to the queue. This is the next run of the queue.
This is actually the next run of the queue.
Is one run of the queue.
Oh.
So if you think about it, the timer active with 9 was because ES entry function, which does an ES timer in it, generates a timer active command, a timer active event that gets posted to the queue. So that's why that's the next run of the queue. All right, that goes in. And we can do this now, for instance, I'm into hiccuping, and what happens if I put it on charger? So that's event number 11. And when I send that in, boom, so now I wasn't hiccuping, I got on charger, that caused it to do hiccuping, exit, to do charging, entry, and then it got a timer stopped, and a timer active. Right, that was the entry function to run toothbrush in charging with ES entry. Okay? And so this is it. So now you can see we've got the code, we have our ability to test it, everything works just fine. Alright, so now I'm going to close this, and now I'm going to show you the hierarchical state machine, which gets a little more fun. Okay. So on a flat state machine, this is slick, but it's not so crucial because you can usually figure out where you are with parameters. On a hierarchical, there's just no way. Okay, there's just no way, especially if you go more than a single level deep. Right, then you really get confused. All right, so what we've got here is, so now I'm going to close this project. Close. All right, and I'll show you. So let's go through the templates again, and I'll do it quick. So now we're going to look at the template HSM first. All right, and let's look at its header file, and let me get rid of that. Okay, so same kind of thing, except we have HSM template. They're remarkably similar. Same template state, same init template, same post, same query, same run. In fact, the header file is identical, except I replaced FSM with HSM. That's it. Okay? No different. Now, if I look at the C file, this gets a little more interesting. Notice that I have to have the template and its sub templates included because I'm going to call substate machine run functions from within. All right. So again, here's my current state, here's my priority. In this case, so again, the init function, identical in every way. Nothing changes. The post function, identical in every way. The query function, identical in every way. Okay, at the top level, they're identical. And the run station is also identical except for, so everything is the same. The init, the entry to the init is the same. Okay? The only difference is right here. This line right there. Okay? So this says, if I'm in the first state, this event equals run template sub HSM of this event. So that means that in my state, I call the substate with the event first. Right? The substate machine gets the first call, and it has the ability to return a different event than it just got. You're calling it with this event, it returns this event, but the return this event might be different than this event because it gets to alter right, as it comes back. So if that happens, so if this event type is not equal to ES no event, meaning it was not handled by the lower state machine, then you go ahead and you run your second switch state. Okay? Which then switches on events because the assumption is the lower level took care of it for you, so you don't need it. Now, all events normally get confused. There are two events which don't get consumed. Okay? The two events are ES entry and ES exit. They can't get consumed because they got to percolate all the way back up through the higher level state machine. So really, that's the only difference, right? And so I have this state, I have other state, again, run template sub, right? And then I have this one, in which you didn't have a substate machine, because not all states might be, in which case you would go straight to the switch without having the if statement on top of it. So that's the only difference. Right? And again, same thing where we run it with the exit, switch to the next state, run it with the entry. That's all we have to do. And then the last one I was going to do is the substate machine, okay, which looks remarkably similar. So let's start with the header file. Now here's the only difference. So the substate machine, again, different name, right, still gets ES configured. So the init no longer takes my priority, it's a void at this point, because now you are going to be calling the init. Okay? No longer are you going to be doing it. Instead, you have to call your own, the top level state machine, when it inits, it has to call all of the substate machine inits to initialize. And that's where it has to be done. All right, and then here, we're going to run template, which looks identical except that I put a sub in front of it. All right, so now let's look at its change. So here, notice that the name is slightly different. It is init p substate, and notice that this is in the C file, not in the H file. That allows us to use init p substate in all of them, right? The substate machines, and still have it consistent without having to have them. Otherwise, you need to make them unique. Right? So this allows for substate machines to have repeated, different ones can have repeated names on the names, which still works. All right. Okay. We have our init. Now watch, our init is slightly different. Current state is init p, and again, it runs the template substate with the init event. Okay. And then it goes. Now you'll notice these init events and the entry event and the exit event. Those are in es event.h. I just want to show you what those are. They're right up in here. Okay. Nope, they're not in there.
We're in the changeover, you have to go direct.
Oh, okay. I thought these were.
Nope.
Oh.
Because this is referencing the wrong one.
Got it.
You never actually did build it correctly.
Oh, okay. No problem. It worked on mine, but they were. Okay. Let's ignore that for now. Alright. I'm in the wrong project?
You're in the Telltale project.
Oh, that's why.
Toothbrush project.
Got it. Yeah, that's right, because I'm showing them sorry. I'll show you those in a second. Because I'm just showing the template right now. We'll move over to the hierarchy. Okay. So here we are. Run template sub. Alright, so here we go. Same thing. It looks almost identical. Right, again, if it's an ES init event, respond to it. If it's in the init p substate. First event, this would be the case where you have a nested one. This would be run sub first state HSM. So it would have another substate with another template file that you used. So this would be the third nested deep, right, that you would do. And this would be the case where you didn't have another one nested. Here's what it looks like if you want to post a new event. Right? So here, for instance, I have, in this one, by getting to this state, when I'm in this state with this event, I post an event to my queue, right? And so this is actually getting posted back up because there's only one queue which is attached to the top level state machine. So that's the one that gets the event. Right? So that's how it does it. And you'll notice that you can declare one in here because you're inside curly braces, so you have the ability to declare a new variable, a temporary variable, which will create it on the stack. It will get passed, and then as soon as you hit that one, it will get destroyed.
And that's not the normal way of passing events.
No.
It's much more common is you change the event and pass it back up the chain.
Right. That's the other way. You can just change the event here and return it if it's going back to the upper level state machine. But if you want to, you can post it not just to your own, but you can post it to different state machines to the right.
So if you want to post an event that escapes your current,
right. That means you're going to go all the way out and then back in again.
Well, it'll service that event after it finishes the sub FSM?
That's right.
Okay.
Right. Well, always. It'll always finish the substate machines.
It has to go all the way back to the top.
But it'll.
If you post a new event, if you change this event, then when you come out of the substate machine back into the template here, when you come back, that means that you're going to be coming back from here, and this event is not going to be no event. It's going to be some new event that you changed, that you returned.
In general, you don't do it the way he's shown you.
Right.
In general, you change the event type. You do this when you want to, for whatever reason, jump all the way back to the top immediately.
Where you want to send an event all the way back to the top level state machine.
But that's the only way to get another sub FSM to trigger using an event.
No, you would use that more if you have parallel state machines, where you wanted to run a different one. You don't necessarily have to do it this way. You could also, the other way to do it would be to basically change this event. You would say this event type equals whatever it is, and then at the bottom, look at the last line, it returns this event.
Oh.
So that would then change it for the right there and then running through, but that creates a temporary event in the thing, not one that gets posted back to the queue and run. So you wouldn't necessarily see it in ES-tab. Right. So that's in the tattletale you wouldn't necessarily see it. Okay, so that's the templates. That's where the sub one changes. Right? So that's if you want to, and then again, it does the exact same thing. It calls an exit, switches states, calls the entries. Okay? So this is the template. So now let me close off the templates. So now that we've done that one, all right, I'm going to close this. And now I'll get to, so before I get to hierarchical state machine, let me bring you, so this was the, okay, so this was it in the flat state machine, right, kind of complicated. And now just to show you what it looks like in the, let's just open this one. Oh, it's over here. Oh dear, I went to the wrong spot.
And this unlet is what we're suggesting to the students to use.
Yeah, it's not bad.
For the pre-labs.
Yeah, it's not
so
bad.
The software is actually already on all the lab computers.
Yeah, it's pretty easy to use. So here is toothbrush. Hold on, let me go up one.
Alright,
What's that?
Blipping. Blipping is what we allow us to use.
Oh, okay. Alright, so let me do the top level brushing HSM, which is this one. Okay, so this should open. 1, 2, 3. So there it is. And let me reduce this from alright, so there it is. So here's the hierarchical state machine. And notice that I did this slightly differently. So I have the state name, the entry, the exit functions, and the sub-state machine that it calls. All right? So init resets the sub-brushing state machine. Other than that, entry to off, exit does nothing. Both entry and exit do nothing. In the off state, it calls nothing. Okay? Button press takes us to brushing. On entry, it does nothing. On exit, it resets the sub-brushing machine, and it calls the sub-brushing state machine. Right? On charger takes you from brushing to the power dock, which on entry does nothing. On exit, turns the LED off and stops the resume timer. And then I just reused the same timer. And then here we have the called subcharging state machine. And again, from off on charger. So you'll notice, first of all, that this to this got a whole lot simpler. All right? Simple, easy, less error prone. Okay? So that's good. Yeah. No, it went back to the.
That's fine, but it's the other one that matters. Never mind. Just keep going.
Alright. So now we'll look at the sub-brushing, sub-in-brushing UXF, where are you? There you are, sub-level. Okay. So here is the in-brushing one, which is a little more complicated. Alright, because it's still the, let's see if I can get it over here. Alright. So here we have, alright, so it comes in brushing. The entry to brushing is motor turns on, start the hiccup timer. Okay. The exit is motor turns off. So if the only time the motor's ever turned on is if I'm in this substate. And that's it. Okay, when I go to hiccup, on the timeout, it takes me to hiccup, starts the half timer, increments the count. If the count is less than 4, when it goes off, it comes back to brushing, which by the way, incidentally turns the motor back on. Right? Kind of clever, right? And then you'll notice that here I set the hiccup timer for 30 seconds when I come back in. If you press a button from either of these states, the button press comes in, you get to the pause state, and the pause state sets and starts the resume timer for 30 seconds. Likewise, if I hit the fourth hiccup one, so count greater than or equal to 4, then I get to the done state, that's what that little guy means, right, is I'm done, and he posts a brushing done to the top level state machine, because I'm now done. Right? That's my exit queue. If I get a timeout from the resume timer for my, from the pause state, I also go to done, because I'm done on that one. And if you press the button again, you go back to brushing. So this is, and the idea here is that you say, well, wait a minute, you might have been in the hiccup when you press the button, but since it pauses for half a second, it doesn't really matter. If you press it again, it's going to start brushing again. It's not going to, it's going to say, hey, you did that part. Right, you're done. And notice that it doesn't reset the count. Okay? Now, interestingly enough here, right, where does the count get reset? The count only gets reset up here. When I exit the brushing state, that's where I reset the sub-brushing count. That's where the count gets reset. Right? So again, I don't have to worry about it below. You know, it's clean up, and a lot of the sort of the bookkeeping is kind of done automagically if you can just sort of keep it in your head that way. All right, and then I've got the other one, it's the cheesy. I'm going to do it this way. Hold on. Oh, let's see. There it goes. Okay. So the last cheesy one is in charging. So that one's going to open in a second. So there it is. Like I said, this is probably not the right way to do it with the timeout pinging button, but actually have the events take you back and forth. But the same thing. Here we blink the LED. Here it's steady. We just basically, on both times, this one when we exit, we turn the charger off. And so you're going to drop in, check, and you're going to keep ping-ponging back and forth. So that's
the right way.
The right way to do it is you actually have on init, you check your state whether you are charged or charging, drop into the right one, and then the only thing that transitions you out is done charging takes you from charging to charged, and battery low, right, below charging takes you back the other way. Right? So the idea is that you don't have because your event checkers are still running, and that was the one we check the A to D state, figure out where you're in, and then post the proper event. Okay, so that would be the right way to do it. I was just doing this in a slightly cheesier fashion. Okay. So now, very quickly, let's take a look at the implementation of it. Alright, so now, where am I? Let me close the S. Okay, so here I am. So now, by the way, I can show you what those events look like. Fine. There it goes. Come on. There we are. Okay. So notice that an init event is an ES event of ES init with 0. An entry event is an ES init event is a cast of an ES init of an array of entry and 0. So the reason we do that is they really are constants. But it's difficult to make a constant struct. So rather than put this in the code, we found the fun because they're easy. Right? And that way you get sort of a nice clean thing. Okay. So going along, so let's take a look at the top level state machine. So here we are. So let's look at the header file. Again, all I'm going to do, change the name. Here again is where I put all of my things, 2 minutes, so 2 times 60 times 1,000, right? So 30 seconds, half seconds, charge check time, 3 minutes. Yeah, these are just sort of constants that I'm going to be using for the timers. Times to hiccup, 4, right? I don't want to do that. Fully charged, 5,000 millivolts, I don't know if you use it. And then sort of all of these would normally be handled by other files, right? But I'm testing whether it works or not. So that's where we're going to do it. Alright, and then here's my enum, which has off, brushing, and power dock. That's it. Okay, and then again, I renamed init, renamed post toothbrush, query, and run toothbrush. So that's it. Those are done. If I look at my C file, here's where the fun comes. Alright, so again, this state names here, this is sort of automatically generated with Max's clever little auto hotkey macro. Alright, so that's how we figure out, that's how you get the nice names printed out on the trace, which is useful. It really is useful to do. Okay, so here's the init, okay, which again, remember the init really, this part is really called by the framework, and all it's going to do is it's going to do run with an init event. Alright, so here's going to be the, so again, post, query, no changes, and so here's the fun part. Okay. So now we're going to run the toothbrush. So on the init event, I'm going to init the sub in charging and init the sub in brushing. Right. And then current state is off, and since off has no entry, so in the case of off, ES entry and ES exit do nothing, and because they do nothing, then I don't then bother to make a transition in because I don't need to. Right. Now, so in the case of off, right, if it's on charger, it goes, the next state is power dock. If it's button press, the next state is brushing. And that's it. That's all it does. Right? In both cases, those are transition. And any other event is ignored. So that's kind of cool. Right? So simple, easy. Right? Now brushing, okay, so I'm in the brushing. Whenever it gets called, the first thing it does is call run sub in brushing HSM. Right? See if it handles the event. And then it says, okay, what events are left that I handle that isn't handled below? Well, I've got an exit, which So remember I need to reset it? Well, that just means run the init sub-brushing state machine. Right? Handles all the initialization. Right? Resets it to clean and fresh. If I didn't call that, the next time I came in, I would come into the sub-state machine at whatever state I was already in. Because it's static, it keeps it. Right? So this allows me to, if I want to reset it when I come back in, or if I want to come back to where I was, this is the choice. If I want to reset it, then on the exit I call the init of the sub-state machine. So here it is. So done brushing is one that gets posted to the top, and so the next state is off, transition is true. On charger, next state is powered off, and on entry I don't do anything, and so entry goes with default. I don't do anything. So again, these are, they're all pretty straightforward. That's it. That's the whole thing. Right? And then, simple as could be. Right? So now let's look at the sub in brushing. Alright, so here's the sub in brushing. Alright, so let's start with the header file. Okay, so again here I change my name to sub in brushing. Coming along. Alright, so init sub in brushing void and run sub in brushing HSM. That's it. And 2 name changes. Get rid of that. And let's take a look at what they do. Alright. So again, this state names, because this is a static, it can be different, right? And the type def, because it's in the C file, can have repeated names, so that's okay. Actually, no, it can't, because I had to change brushing to in brushing here in order to make it, because it said, wait, you already have a state, you already have an
The highest level can't be duplicated.
Yeah, the highest level can't be duplicated, but you can duplicate among substates as you like.
And this is showing off that. This is showing off that init p states need to be in p substate.
Yeah.
You don't have an init p state.
From the above, exactly. So that's why it has to be different. And if you made another substate below that, I'm not sure if you would have to or not.
No.
But no, because that's within the lower levels are fine.
If you want to add for a recent query to your global state machine,
then you need an unique one. Right? So we left query out for the lower level, but you could call it if you wanted. But that means you need to reveal the enum, and that means you need to have unique names going through. Alright, so here we go. So my static in brushing substate and my current hiccup count is there. Alright, so here's the init. So again, it just calls itself with an init event. And then here we go. Okay, so here is the init event. And all it says is hiccup count goes to 0 and current state is in brushing. So that's where we reset the hiccup count. Right there on the init to the run in brushing. And if I'm in brushing, turn the motor on, start the timer for 30 seconds, right? On exit, turn the motor off. And on button press, take me to paused. And on timeout, if it's the hiccup counter, take me to hiccuping. If I'm in hiccuping, on entry, increment the count, start it for half a second. On exit, so restart the timer for 30 seconds. On button press, take me to pause. Okay. And on the case of the timeout, this is the only one that's complicated, right? It says, okay, first of all, make sure it's the hiccup timer, because that's the only one I want to respond to. Right? And if it's less than time to hiccup, then I'm back in brushing. If it's not, I'm done. And the transition is true. Now this is an interesting one. So paused, again, on entry, we start the resume timer. On exit, we stop the timer. And if the button press, we go back to, remember, button press, we go back to brushing and we have an exit, so we'll stop the timer. Alright? And if it times out and it's the resume one, then the next state's done and transition is true. Now this is an interesting one because remember, so the 2 ones that switch me to done, right? So on done, right, on entry to done, right, I go ahead and post a done event and that's it. That's the only event I respond to. I say, wait a minute, there's no way to get out of state done, which is correct. Right? So you wind up after 2 minutes or after 4 things or after pausing for too long, you are in done. Done posts the state, post the event, done brushing to the hierarchical state machine to the top level, and done brushing tells it, oh, that means brushing exits, which means it resets the low level state machine. So all the cleanup and everything else is done that way. So it makes it
the higher level it calls it in again, which resets all.
That's right, which resets it. Right? So the higher levels exit. Remember that this one, when it exits brushing, so let's look at powered off brushing. So on exit, it reinitializes the second one. So notice how easily it cleans everything up. Right? So there it is. So that's the whole thing. And there's the other one. So now, since we've never done this before, we'll go ahead and,
Brilliant plan.
Brilliant plan.
Well, the Tattletail keyboard are working fine.
Exactly.
It has all these events set up correctly.
Yeah, and so nothing,
Oh,
What?
I might know why they print out that event.
what?
I need more wallet transmit empties.
Oh, okay.
My battery filled the buffer.
Oh, cool.
255 or 512 with not that many characters.
Okay, so I'm going to now, so we ran it, so now all we need to do is change this one. So we need to go,
We have to use it.
huh?
Yeah, because it's
Yeah.
the HSM now.
Right. So now we're flat, back to the sandbox, into the hierarchical. So now what you get to see, distribution, default.
That's hilarious and stuff.
Now you guys get to see where the Tattletail really becomes useful. Alright, and away we go. Alright, so watch the initialization here.
Yeah, that's the fun one.
Boom. Okay, so this is good. Alright, so IO stack initialized, starting toothbrush state machine, using second generation events, errors 0. Okay, so here we go. So run toothbrush 8% starts out in an init state and gets an init 0. It calls run sub in charging in an init substate with ESInit. It calls run sub in brushing with an init state. So so everyone just got initialized. Right? So not only did the top, but the top called the bottom too. Right? And so they all initialized. And right now, we entered into the offset and it said, oh, by the way, timer active on A, which is 10. Right?
Those
So,
arrows are spanning from run toothbrush HSM, right? Not
Yeah.
the sub.
right.
If the sub were to have an event.
You would get another one in there and it would keep going down.
Okay, so you check in.
Because
Yeah.
its initial P states is initializing.
At least the P states is a little funny.
It's
So,
initializing all of the initial substates.
right. Alright, so we're in off state right now. And so let's see what happens when we do a button press. Well, first of all, let's see what happens when we give it a timeout event. Alright, so let's give it a 7 and a parameter of 9, which is our timer. Right? And so we do this, and basically it says, look, run toothbrush HSM got called with an ES timeout event of 9, and it did nothing. Right? No transitions, nothing. That was all that happened. That's what happened. All right. So now let's see something interesting that happened. Let's call it with a button press. So here's an event 10. All right. So we're going to press the button, which should take us into the brushing state, which should take us into the sub-brushing state and move us into brushing. So here's 10. Boom. Okay. So, and again, this stuff where it says you see the recursive call started, counted, and ended, that's going to disappear from the thing. But here we go. Run toothbrush HSM off button press, goes run toothbrush off with ES exit, calls run toothbrush brushing with entry, calls run sub in brushing with entry, right? And then that one gets, and then here we have, because that triggers 2 timer active ones because the timers get turned on. Right? So they're the timer active event comes back. Not quite sure why we had it twice, but probably my coding. So anyway, and it just, by the way, that lets us know we triggered a timer. Right? So that's cool. So now the next thing we want to know is if the hiccup timer goes. Right? So that would be an ES timeout with the hiccup timer. So an ES timeout is event 7. Right? And the hiccup timer is 9. So let's see what happens,
And broken. You didn't update your events. This is what happens.
Oh, this is what happened when I didn't,
Yes.
Okay.
So, welcome to...
Right.
This is
So, this is actually good debugging.
what happens when you do not have those arrays set up correctly.
Right. So if you don't have the array set up correctly, you'll get into a thing where it sort of just locks up somewhere. Right? And you can't tell what went on. And so the first thing you guys should do if you ever see this, alright, is close it, clear it, go to the project, and you say, okay, where did I not have this? And it's going to be either in,
Most
likely in the toothbrush HSM, right there. No, that one is good. Sub in brushing. Probably this one that's, do I match? Done. No, that one's right. And let's look at, is it the other one? So I've been charging.
Could be a different one.
I haven't called it yet. That doesn't necessarily mean we, not yet.
Click on the name date, not the little thing.
There we go. Alright, and this one has, no, those are good. So, I bet you I know what it is. I know where it is. It's ES, no, it's ES, an ES configure.
You added an event, didn't you?
I added an event. Alright, so let this be a lesson to you.
This is why the macro exists, because you just rerun it.
Right, so this one probably doesn't match.
I should let that out then.
What's that?
Get rid of the output.
Oh yeah.
Yes.
So the right thing to do here is to grab this, copy it.
This will be an icon on your desktop. You just have to find it.
I have to find it in the Dropbox.
Sandbox.
Yeah. Come on up. Oops. Sandbox, macro generation, generate string form. Okay. So this is where I ran it. It said, please paste below the event list.
So copy what it auto generates.
And I'm going to select this and paste over it and do, Control V. So notice that I went from 16 events to 14 events. Yep. Alright, so notice that I got something wrong. So this is what we call a group 7 equipment not at fault. Alright, this is a,
that's why it keeps track of the number of events,
right.
Essentially, so it won't try if it's outside the event range.
But unfortunately, I tried outside the event
Will
range.
that script generate that part of the code?
Yes. No, that's all from the script. That script generates exactly that, and the same script generates your state names. It parses what you put into it and figure it out.
Okay.
So what is, did the whole thing locked up, or was it just a terminal?
We basically did a printf on a string that had no null termination character.
So
it random walked through memory until the stack blew up. No actual good way to trap that error.
Yeah.
Okay, and does the whole stack lock up? Or is it just...
It doesn't really matter one way or the other. I mean, you're off in memory somewhere. Right. You're done. You at this point, you're out of bounds.
I can't fix that to a degree.
Okay. So now what we're going to do is rewrite it.
I have a question.
Yeah.
When you print up the stuff on here where you have all the events, it looks like in the last one and this one, the very last event is IIT.
That was because there were 16, because I had done that part wrong.
No, in the last.
I believe that's because I pinned it in to record a bit too much. That would be a minor glitch that I can fix.
Alright, so once again, we're running again.
512 characters is not that much once you really realize it.
Yeah. Okay, so here's our list. Here's where we are. Alright, and again, let's now let's start with button press again. And now the neat thing is we were actually we just got shown an error that I had, and it trapped it in an odd way, but it still trapped it and let me know I had an error.
Alright, you know I recursive calls.
What's that? Yes. Oh, you fixed it already?
Yes.
Okay. So Max already suppressed the recursive calls before I got that working out of Dropbox. All right. So here we go. So we ran button press. Right. So we ran toothbrush off, button press, run toothbrush off, ES exit, run toothbrush off, brush and entry, run sub with entry. Right. And so there it goes. And then we get a timer active, which then runs. So we get 2 timer actives for a reason probably that will show up in my code. And now we wanted to do a timeout on timer 9, right, which is the hiccup timer, right? And if we do that, hello, oh no,
You rewrite it. I think your list of ES events doesn't match what happened in your stage.
That's probably it.
I think you have 16 events, but you haven't listed them all in your ES events.
I have events that are
well.
Yeah.
You now have another property debug.
Yeah.
Fixed before.
Exactly. So something to get to, but you guys get the idea. All right.
I'll fix it for Thursday.
Yeah. It might actually be my code that's
That's
wrong.
myself.
Yeah. So we'll trace it down. Let's do a different trace through. See if I lock it up the other way. But the idea here being that it's, all of a sudden we are getting, so let's see if we go through event 11 on charger, which takes the other way. If it works, okay. So off gets on charger, goes to toothbrush with an exit, goes to toothbrush entry to power dock, which does an entry into charger. Okay. So at this point we should see if I do a power button right now, button press, it should do nothing. So if I do a 10 here, boom. Okay, so basically it says it got a button press, which handed the button press to the lower level state machine, and it did nothing. No exit, no entry, essentially no response. All right, but you can see the call chain, right? And it gives you the name of the function, right? This is key, right? So you can actually know which function got called. So this is nice. All right, so now the way I get out of this is I have to take it out of the charger. All right, so this would be 12. All right, so I do that. Okay, so here we go. So now we went out of the charger. All right, so out of charger with parameter. Here we go. Power dock out of charger 0 sends an out of charger event to the lower level state machine. The lower level state machine doesn't actually use it. Right, so the upper level state machine says, right, I'm here and I'm taking an exit. And it's going to call an exit on the lower level state machine, and then it's going to cause an entry with state off on the higher level. Right? And then the one timer stopped, the other timer active. So remember, when it gets there, it kills the resume timer, which is time ready. Okay. And then again, if we want to do a button press, right, so if I want to say, well, I'm confused, I don't know what events I have anymore. There they are. And if I want to do button press, so that's 10. So now I'm back into brushing. And if I want to say, if I press the button again, right, I should head to pause. Oh. Interesting. I think we're flooding the buffer.
Shouldn't be.
Right. We'll play. Anyway, so that's where we are. So we'll get this working by this week because the kids are going to be using this, which means you guys are going to be spending a lot of time doing this. Right. Yeah.
Just for a sanity point of view, is it possible to put a return character for from state passing passive actions that was coming?
It already has paragraphs.
Yeah.
I know right now you just have a key block of text.
Oh, you
white
want
space
one?
Yeah. All right. So there it is. And what's interesting is all I did with this code when writing it was get it to the point of compilation. Right? So we were sort of debugging it kind of on the fly. And so yes, we're getting errors, but right now we're not sure where the errors lie. But this is how we debug it, and this should make their code go vastly better, right? And the reason I want to get them to get a hang of this now, even though it's immensely painful in the first week, is because they'll learn it, and then when they get to the project, it'll help a great deal, right? So this was, and kudos to Max here because this was about 3 weeks of his work.
Hit
compile again?
Yeah. Yours take.
Yeah. Hold on. 20 seconds later? I can close my DS30. Do you want me to relaunch that?
No. Sure. Just reload it.
Okay.
So is the lab all written up?
Yeah. To a degree. Yeah. We've been revising.
We can probably kill the recording now.
Yeah, we'll try one more time.
It's still going to exactly where it is because I'm not at that point yet.
Oops. Oh, you guys don't see this. I see this. Alright. Okay. So there it is. So
now send an event.
Let's see. It's send 10. Send a button press. Boom.
You glitched my code out.
Sorry. Okay. Anyway, that's what we wanted to show you. So from here, that's kind of it. And
no, you're using all copies. Weird.
Okay. That's just built clean, so I shouldn't.
I know, but
all right. we'll sort it out. In any case, that's where we are. So I'm going to stop this, and I will actually post this